All right, hey everyone, welcome back to our next lesson. Today we're going to talk about a very important topic, average rate of change. You are definitely going to see it in calculus next year. So we're going to brush up on it today. You might remember from Algebra 2, so it was covered then, but we're going to go into a little more depth in it in this lesson. Your aim for today is how do we find the average rate of change of a function. Your homework is in the OpenStax textbook. It's page 48, numbers 9 to 13 odd. So 9 to 13, those odd problems only, and then also 16 and 17 on that same page, page 48. And then on page 49, there's a problem I want you to do, 27, that has to do with population change and average rate of change, right? So please complete these problems. All right. With that being said, though, let me get to the do now. All right, so here we are. So first part is if you drive a distance of 120 miles in 2 hours, what is your average speed? And secondly, if the distance you walk in relation to time t, given by the function d of t equals 3, 2 plus t, what is your average speed from t equals 1 to t equals 3? And how about from t equals 1 to, I know this is a weird time, but that's intentional, so t equals pi, right? So literally like the number pi. And yeah, we're going to explore how that relates to average rate of change. Okay. All right, let me get to the solution now. All right, so here we are. So first part was if you drive a distance of 120 miles in 2 hours, what's your average speed? So we're just going to use, right, speed is distance over time, right? So that's 120 miles over 2 hours. So that'll come out to 60 miles per hour for part one. And then for the second question, we're going to use, so the numerator, right, if you notice, that's the difference in the distances. So we're going to calculate the distance at after 3 seconds. Well, I guess I should clarify. It's not necessarily seconds, right? They don't give units here, but 3 units, right, minus d of 1 unit, and then divided by 3 minus 1. And then d of 3, if you plug in 3 into this function here, you're going to get 9 plus 2, which is 11. That's right here. And then d of 1 is 5, right? So 3 times 1 is plus 2 is 5. Okay, so in the numerator, you're going to get 11 minus 5. And then in the denominator, it's 3 minus 1, right? So this should be ringing some bells, right? This is just slope, actually, right? So change in y over change in x, right? So we're going to evaluate the function at both x coordinates, 3 and 1, and then divide that by the difference of those x coordinates. Okay, so it'll be 11 minus 5 divided by 2, which comes out to 3 miles per hour. Second part was with regards to t equals 1 and t equals pi. So this is going to look a little weird at first, but it's actually not that bad, right? If you plug in pi, you're going to get 3 pi plus 2, right, in this function, 3 pi plus 2, and then minus 5, right? So same evaluation of 1. And then in the denominator, it'll be pi minus 1. Okay. Now you might be wondering like what we do with the pi, but it actually divides out. Okay, so in the next step, you'll see that it's 3 pi minus 3, right? 2 minus 5 is negative 3. And then denominator is still the same. And then from here, we're going to factor out a 3 in the numerator. So we get 3 times pi minus 1. And then the pi minus 1 factor divides out. And we're just going to be left with 3. Okay. And as a follow-up question to that, so what do you notice about the two average speeds in the second part of the do now? Okay, so this part, right? So if you notice, right, they're the same, right? It's both 3 miles per hour, okay, which I say here. So the average speed for a linear function, right? This is a line, right? 3t plus 2, right? Y-intercept of 2, slope is 3, right? The average speed for a linear function is the slope of the line, and it remains constant, right? So you're gonna have like a line, right? And the slope is always the same, right? It doesn't change, versus a parabola, right? So let's say you have a line here, right? Slope doesn't change, right? But for a parabola, right, the slope does change, right? So like at this point here, the slope is negative at that point. And then here on this side of the parabola, the slope is positive. Okay, so different things, right? So for the line, the slope does not change, right? It's always 3, at least in the case of the do now. And then for a parabola, the slope does change. Okay, So that's the concept we're going to explore today. All right, so let me just give you an overview of the rest of the lesson. So we're going to talk about, yeah, another average rate of change problem, but generally, right? Some follow-up questions to that diagram, and then we're just going to define average rate of change right here, and then that's going to be followed by your classwork. Okay. All right. With that said, though, let me get to the slides. All right. Let me zoom out for this. All right. So here we are. So suppose you take a road trip and record the distance you travel every few minutes. We will define the function as follows: S of t equals total distance traveled at time t. All right. So this graph here. Here's the resulting graph. So first questions are as follows: how many miles have we traveled after 1 hour? Okay, so after 1 hour, right? So you just go on the x-axis 1 hour. You'll see that it's 50 miles, right? So this is 50, this is 100, 150, 200, right? 2 hours, right? After 2 hours, so go on the x-axis again. It's about maybe 75 miles, right? That's right here. After 3 hours, we can say it's maybe 125, right? Let's go over to here. And then the y value for 4 hours, that would be 200. Okay. And they also label on the diagram that the change here on the x-axis is 3 hours, and the change in the y-axis is 150 miles. Okay. But we're going to get to that later. All right, let me show you the solution. So yeah, part A was 50 miles, and then after 2 hours it was 75. This answer was from the textbook. Actually, it was 140. I mean, you don't have to be too precise, but I estimate it to be 125. But yeah, 140 is what they said. So I guess I'll go with that. The last thing was 200 miles. Okay, yeah, that's what we expected. But anyhow, your follow-up question to that was find the average speed between 1 and 4 p.m. Okay, between 1 and 4 p.m., what's the average speed? All right, so average speed, just think of the formula, right? Distance over time. So the distance traveled over the time elapsed, right? That's right over here. And they actually already do the math for you on the diagram, right? It's 150 divided by 3. All right, so that'll be 50 miles per hour. Okay. And then for the follow-up questions to this, I'm not going to show you the slides just because we're going to go back and forth. So I'll just show you the question on my lesson plan, and then we'll jump into the solution. But yeah, here are the answers for this first example. And then the second example, the answer was 50 miles per hour. Okay. If you need to copy this, please pause the video here. All right. All right, some follow-up questions. Let me zoom in for this. Okay, so how would we express this in function notation, where the function is s of t? Okay, so average speed. So if you remember, right, so the last question was find the average speed between 1 and 4 p.m., right? So it's distance traveled over time elapsed. So what we actually did, though, was we calculated s of 4, right? We plugged in 4 into the function, calculated the distance traveled, which was 200, and then we subtract the evaluation at 1 p.m., right? So that's 50, and then divide that by the difference in hours. So that's 4 minus 1, that'll be 3 hours, right? And then that's how we got 50 miles per hour. But this function notation is what we're going to use for our average rate of change formula. And yeah, this should be looking really familiar right now because this is just slope actually, right? As for why we're calling it average rate of change, I'll get to that in a sec. But yeah, just keep that in mind. We're going to be using this notation for the rest of the lesson. Okay, the next question to that was express the average speed in function notation for between 2 and 3 p.m. Okay, so we have s of 3 minus s of 2, right? Just plug in 3 and 2, right? And then divide that by 3 minus 2, the difference in time. And then, right, s of 3, on the graph, it kind of looked like 125 to me, but we'll just go with what the textbook said, 140, right? And then s of 2 was 75, right? If you want to confirm that, right, s of 2 is 75 here, right? And then s of 3, they were saying is 140, okay? And yeah, we just divide that by 1, right? 3 minus 2. We're going to get 65 miles per hour. Okay, so 145 minus 75, that's 65. Okay, all right. But with that being said, let me get to the definition of average rate of change. Okay, so here we are. So you don't have to copy this italicized part down. I'm just going to say it. This is what I would tell you in class. Finding the average rate of change of a function is important in many practical situations, such as knowing how fast the air temperature is dropping as a storm approaches, or how fast the stock price is increasing after a major upgrade to an app. We define it as follows. Okay, and for this, I'll get to the slide. Okay, because this is the part that I actually want you to copy. All right, here's the slide here. Zoom out. All right, I'm going to have you copy the definition first. I know it's a long one, but after this, we'll get to the classwork, okay? And then there's also a table, or not a table, a graph that I want you to copy. It's a good diagram for you to visualize average rate of change. But yeah, I'll get to that next. Okay, so here's the definition. The average rate of change of the function y equals f of x between x equals a and x equals b is average rate of change equals change in y over change in x, which equals f of b minus f of a over b minus a. Okay, so this should be ringing bells, right? This is the same thing as slope, right? So the only difference here is average rate of change is the terminology we use for functions outside of lines, right? So if you remember from the question earlier in our lesson, right, for the line 3x minus 2, the slope is always 3, right? For a line, the slope is always the same, right? The slope's not going to change. But for other functions like parabolas, maybe like x cubed, x to the fourth, pretty much like every other function besides lines, the slope is going to change throughout the function. Okay, and that's just the terminology we use for those functions. Okay, so when you think of slope, when you hear slope, when you hear slope, think of lines. When you hear average rate of change, which is our vocab word for today, think of other functions besides lines. Okay, so slope, think of lines. Average rate of change, think of other functions besides lines. Okay, but yeah, as you can see, they have the exact same formula, right? F of b minus f of a over b minus a, right? Changing y over changing x, same thing. Okay, the only difference is the context, right? Slope line, average rate of change, other functions. All right, back to the definition. The average rate of change is the slope of a secant line between x equals a and x equals b on the graph of f. That is the line that passes through a comma f of a and b of f of b. Okay, so I'm going to show you what this all means. So this has to do with the diagram below. Yeah, but let me. Okay, so well, I'll copy this definition first, and then I'll explain in the diagram. So yeah, if you need to copy this, please pause the video here. Okay, and really quickly, just secant line. That's a vocab word that you might have seen in geometry, right? And it's a word that you'll see again in calculus. Okay, so this exact same like lesson is going to show up in calculus. All right, with that said, let me get to the diagram. So the secant line, at least in the context of this diagram, is the dotted line here, right? So it's the line that connects a f of a, right? So a f of a is this point right here, and then b f of b is that point right there. Okay, so a f of a is this point, b f of b is that point, and then the secant line is this. Okay, and we're just finding the slope of that secant line. All right, so I would actually copy this diagram down. So just draw your y and x axes, your 0, and then a and b, and then the corresponding y values, right? F of a, f of b on the y-axis. Draw this general graph here, and then you have these 2 points, the secant line, and then note here that the difference here is b minus a, right? That distance here is b minus a from here to here, right? And then the vertical distance from here to here is f of b minus f of a. Okay, and then there you have it, right? Average rate of change. it's change in y over change in x. So it's f of b minus f of a, right? This vertical distance divided by b minus a. Okay. All right. To copy this down, please pause the video here. Otherwise, I'll be moving on to the classwork. Okay. So here's a general look at the worksheet. Yeah, we're just going to find the average rate of change for this line here. And as you know, right, the slope of the line should always be the same, right? It should always be 3. But we're going to actually calculate these to show you that. And you're going to see that in each case, the slope, or in this case, as I say, the average rate of change is always going to be 3. Okay, and then, yeah, follow-up question, which I just explained. And then 2, 3, and 4, we're going to find average rate of change for functions that are not lines. So the slope is not constant. But yeah, just to practice with that formula. Okay. All right, let me get to the solutions. All right, number 1. So average rate of change for between x of 0 and x of 1 is f of 1 minus f of 0 divided by 1 minus 0. Okay, f of 1 is going to be 3 times 1 minus 2, which is 1, right? So that's here. And then if you plug in 0, you get negative 2. So that's minus negative 2, which comes out to positive 2. So that'll be 1 plus 2 in the numerator. And then in the denominator, it's going to be 1 minus 0. That'll be 1. Okay, so 3 divided by 1 is 3. That's your first answer. Part B, it's 7 and 3. Okay, just 2 different numbers. So f of 7 minus f of 3 divided by 7 minus 3. 4 in the denominator. Okay, and then if you plug in 7, you're going to get 3 times 7 minus 2 in this function. That should come out to 21 minus 2, which is 19. And then we have 9 minus 2 here for f of 3. Right, 9 minus 2 is 7. So it'll be 19 minus 7, which is 12. Okay, so 12 divided by 4, that's also 3. All right, next we're going to have this general variable evaluation. Okay, so it'll be f of a plus h, right? That's the second point. And yeah, you always want to evaluate the second point first because that's your ending point, right? So evaluate the ending point and then the beginning point. Okay, so f of a plus h minus f of a over a plus h minus a. Okay, so if you plug in a plus h into this function, just be careful with the parentheses, right? So 3 times a plus h, we're gonna have to distribute that 3 minus 2. And then for f of a, it'll be just plug in a, right? So 3a minus 2 minus 3a minus 2. And then in the denominator, it's going to be a plus h minus a, which will come out to just h. All right, now we just simplify. So just be careful with the distribution, right? So we're going to get 3a plus 3h minus 2. That's right here. And then minus 3a plus 2. That's here, okay? And then divide that by h. So a lot of things cancel out. You get 3a minus 3a is 0, right? Negative 2 plus 2 is 0. And then you're just going to be left with 3h. Okay, so it's going to be 3h divided by h, which is just 3. So as you can see, right, as promised, each of these answers is 3. And the follow-up question to that was, what do you notice about all 3 average speeds? Explain why they should be so. They're all the same, right? Oh, I guess I should add that in. All 3 average speeds are 3. Okay. And then the explanation for that is the average rate of change for a linear function f of x equals mx plus b, or y equals mx plus b, is constant and is the slope m of the line, right? So as you can see, it's the slope 3, okay, which matches up with our answers, as it should. Okay, if you need to copy down any of these solutions, please pause the video here. Otherwise, I'll move on to question 2 through 4. Okay. All right, question 2 here. So this function is a parabolic, right? 1 minus 3z squared. And then we're going to evaluate from z equals negative 2 to z equals 0. Okay, so evaluate f of 0, right? So if you plug in 0 into this function, you're going to get 1 minus 3 times 0. So that's 1 minus 0. And then the second part is -2. Just be careful with the negative sign. Plug in -2 here. You're going to get 1 minus 3 times -2 squared. Okay. And actually, let me be careful with this. Actually, write out the calculations overall. Sorry. Okay, so that'll be 1 minus, okay, let's see here. So 1, so this is 4, right? -2 squared. So that's 4. And then 1 minus 3 times 4, that's 1 minus 12. Right, 1 minus 12, that's -11. And let me put that entire thing in parentheses. And in the denominator, right, 0 minus -2. So that'll be +2. Either way, you're going to get 1 plus 11 in the numerator, that's 12, and then divide that by 2, you get, you get 6. Okay, so 6 is your answer for question 2 here. All right, this is going to be followed by a few general variable evaluations. So the reason I'm emphasizing this is you're going to see a lot of these questions, these exact types of questions in calculus. So you might very well see like this exact 1/x function being evaluated here. Okay, so let's go through it. So we have x equals 1 and x equals a. So it'll be 1/a, right? Evaluate the ending point first. So 1/a minus 1 divided by 1 divided by the difference, a minus 1. Okay. To get rid of the denominator, I'm going to multiply by the LCD, lowest common denominator, which is just a here, right? So a over a. And then in the numerator, you're going to get, so this entire thing times a is a divided by a, which is 1. And then 1 times a is just a, right? So you're going to get 1 minus a in the numerator. And then in the denominator, it's going to be a times a minus 1 here. Okay. And then here, I actually factor out a -1. The reason for that is I want to divide out this factor here. So if I divide out -1 here, you can rewrite this as -1 times a minus 1. And you can check that, right? So that's the same thing as this, right? So -1 times a is -a. That's this part here. And then -1 times -1 is +1, which is accounted for here. Okay. Yeah, so I just factor a -1 so that I can divide out this a minus 1 factor. And if you do that, you're going to get -1 divided by a as your final answer. Okay. All right, lastly, we have question 4. Let me get rid of that blue line. Okay, so 2/x plus 1, x equals 0, x equals h are going to be the points of evaluation. Let me zoom in here. Okay, so f of b minus f of a over b minus a, I just wrote the average rate of change formula. So evaluate at h, right? It'll be 2 over h plus 1 minus 2 over 0 plus 1 divided by the difference, h minus 0, which is easy enough to just h, right? So this right fraction here, it's 2 divided by 1, so that just be 2. And then from there, I'm going to multiply by the LCD, right? The only denominator here is h plus 1, so I'm going to multiply by h plus 1 over h plus 1 to get rid of the fraction. And then, so 2 over h plus 1 times this is just 2, right? And then -2 times h plus 1 is that. So you get this in the numerator here. And then in the denominator, you get h times h plus 1, which is shown here. Okay, now we just distribute 2 minus 2h minus 2. Okay, and then a bit more of the math here just to show you. 2 minus 2h minus 2, right? That's what we get here, right? 2 minus 2h minus 2 divided by h plus 1. Okay, and then 2 minus 2 is 0, right? So you're just going to be left with -2h. And then in the denominator, right, still the same thing. And lastly, you can actually divide out h, right? So the h variable divides out. So your final answer is going to be -2 divided by h plus 1. Okay. And let me zoom out a bit for all these solutions. So if you need to copy down any of these solutions, please pause the video here. But yeah, that's all I wanted to say for today. Please remember to submit your homework, and I'll see you all tomorrow. Have a great rest of the day.